This example has us find the total solution of a simple spring mass damper system that is being affected by this sawtooth forcing. So in the end, we are interested in finding the full x of t. And we'll define what that x of t looks like once we get into our modeling. Okay, so what we're going to have here is we're told it's just a simple spring mass damper system, and some of the work is done for us. We're told the k and the c and the m, and we're going to define x as positive down, and there's going to be this forcing acting on the top. So the equivalent m, c, k are given. I will recopy them here. So we don't need to use Lagrange's equations, anything like that. That work is done for us. There's still plenty of other work that we have to do in this problem. So at least these parameters, these system parameters, are already given. So now we want to work on the forcing function. So we see graphically it's given to us. It is not just a simple harmonic. It's not just a single sine function or a single cosine function. So this falls into that general forcing category. One way to solve it is going to be to do a Fourier series expansion on this f of t, and then use the techniques in this subsection. So in order to do that, looking ahead, thinking ahead, we are going to need to know the coefficients of the Fourier series expansion. If we know those coefficients, the a terms, the b terms, then we're going to have a procedure in order to assemble our steady state solution. We can apply our initial conditions, and then we can get our total solution. So let's look at this f of t, and this goes back to what we talked about in section 1 when we were looking at Fourier series expansion. What we're going to need to do is be able to define f of t, and in this case we're going to be able to do it as a piecewise function. We can define the period. If we look at this, it's going to go, for the first 2 seconds it's at 0, and then it's going to jump up to 500, then it's going to go over, and then it jumps back down to 0. And then that's going to repeat itself. If you notice how I drew it, I put an open dot at 0 and then the closed dot at 500. It really doesn't matter which one, the way we define it. Is it 0 at 2 seconds or is it 500? At that exact moment in time, for our analysis, it doesn't actually matter. But what we do care about is we want to find what is that smallest repeating pattern. And if we look at this, that smallest repeating pattern is going to be 5 seconds. Right? From 0 to 5, and then that same pattern of a dwell at 0 and then a dwell at 500 keeps repeating itself. So our t is 5 seconds, which makes that fundamental period 2 pi over 5 radians per second. And our f of t, then, we can define. It's going to be just a value of 0 for t less than 2. And I only have to define f of t on my on this single period, the 5-second period. And then it's going to be 500. We're in base units, that's in newtons, for 2 to 5 seconds. And then it repeats itself. But for the purposes of finding the coefficients, I just need to define it on this one period. So why do we care about this? Well, we can right now, we could write our equation of motion. We have our mck, we have our f of t as this piecewise function. While we're in this modeling step, I'm going to do the Fourier expansion of f of t to find those coefficients before I head off to the equation of motion step, identify, and all of that. So f of t, I want the Fourier series expansion of. If we remember back to section 1, well, we can find our a naught is going to be 2 over t, integral 0 to t of f of t dt. So it's more or less the average of f of t on its period, really twice the average of it. All right, so we have this piecewise function. We can do this by hand. We did a similar problem in section 1. The second problem was a sawtooth. It had a little bit different of period. It had a little bit different of amplitude. So we can do it by hand. We can refer back to that. Or in this case, since we've already gone through that, I am going to use Mathematica to do some of the heavy lifting here. Now, in Mathematica, I'm going to define some of these values. So we already know that that fundamental period is 5. I'm going to define omega as 2 pi over 5. All right, so notice what I'm doing here. It went a little bit fast, but for omega, I can use escape, W, escape, and it turns into my omega. And for pi, I can do escape, P, escape, and it knows that pi is, it's built in that pi is 3.14, etc. Right, so I can define t, I can define omega. And now I want to put in my f of t. I can define a function in Mathematica by using the bracket notation. And then I'm going to define this with respect to t. So notice what I have to do to define a function in Mathematica. You need this underscore after the variable name. Right, so it's a little bit weird here, but without the underscore, it's not going to know that you're trying to define a function. And this is equal to a piecewise function. We can do a piecewise function. One way to do it is with escape, PW for piecewise, escape. And this is going to have two intervals on it. I can press Control Enter and have it set it up like this. So I can define each interval. So I want 0, and then this is good for t less than 2. And then it's going to be 500. And I can just have here, because I only have two intervals, less than 2, greater than 2. Actually, I guess I will define this greater than or equal to 2. Then it's defined. And press Enter. So it has this true otherwise, but that's basically the otherwise statement is how Mathematica interprets this. But we can only be on the first interval or the second. So the third is never going to come up. And we can test this out. So f of 1 second should return 0, and it does. And for 4 seconds, we get 500. And for, let's see, 2.1 seconds, 500. All right, so it's working the way it should be. So our piecewise function is defined, our period is defined, and our fundamental frequency is defined. Now let's start by looking at our A0. That is going to be 2 over t times the integral from 0 to t of f of t dt. Again, notice here I'm using f of t without the underscore. The underscore was only for defining it. Here I'm using it just as a function. So I run it and I get that a0 is 600. So I want to record that in OneNote. So a0, I get 600 for my value. And we can go on and find our an terms. I'll just highlight this so that we can come back to it. An was defined as 2 over t, 0 to t, f of t cosine n omega t dt. So let's see what Mathematica gets for us. We can do, again, the same sort of procedure, but now it's f of t times the cosine n omega t dt. And make sure you're putting a space between these variables so that it doesn't think it's one giant variable. All right, so f of t times the cosine of n omega t dt. And we see Mathematica does it very quickly compared to when we were trying to do it by hand. That's really nice. And we have here this sine of 2n pi. Now we know that that is going to simplify down because we know right now that n is always an integer value. It's 1, 2, 3, 4. At the moment, Mathematica does not know this. However, we can tell it to simplify this further. So I'm going to use this full simplify function, and I'm going to say take above. That's what the percent sign is. Percent sign is whatever the result is above. Put that in, and now apply the idea that n is an element of integers. Right, so it's going to take what I have above, and now it's going to simplify it, knowing n is from the integer set. And we see here that it simplifies down a little bit. It takes that sine of 2n pi and it gets rid of it. because we know it's always going to be 0 for any integer value of n. And we have what's left. So let me just reduce this a little bit. All right, so that's our an terms. Simplified down, applying n as an integer, that sine of 4n pi over 5 is not going to simplify down nicely. So I want to record now my an terms was that negative 500 over n pi times the sine of 4 pi over 5 times n. And we're ready to find our bn terms. Bn terms are going to be defined like the an, but it's going to use the sine instead of the cosine. So our bn is 2 over t, integral 0 to t f of t, sine n omega t dt. And once again, I'm going to let Mathematica do the work for us. Copying it down, we get a 500 over n pi times cosine of 4 pi over 5n minus 1. And I just reversed the order from the Mathematica, so I have, it looks a little bit cleaner now. So those are my bn terms. So all of this is just so I can do the expansion of f of t, and then when I do my solution in a little bit, I have the coefficients already found. So a recap, I have my a0, an, and bn, and I did this all using Mathematica, but we could have done this by hand, and we did a similar problem by hand previously. So our modeling step is done at this point. We have our equivalent mass spring constant damping. In fact, it was given to us in this one. And we did our Fourier series expansion of f of t. We have it defined with its coefficients, or just as a piecewise function. And there are different ways we could solve this one. For now, we're solving it using the Fourier series expansion technique. But we actually will revisit this one later and use a different technique to solve it. So let's look at our equation of motion. We have mx double dot plus cx dot plus kx equals f of t. I'll just leave it as f of t here. Again, let's look at the model we were given. It's a simple spring mass damper system. So it looks like every other 1 degree of freedom spring mass damper that we've had. And now we can apply our given parameters as well. It's a 10x double dot plus 220x dot plus 4000x equals f of t. Now we can identify what we have. Left-hand side has only x as a dependent variable, so 1 degree of freedom. It is going to be linear. It is going to be forced, and I'll just call it general forcing. We are damped, and we're going to see what kind we are once we get into our parameters. And we can look at our parameters now. So our general solution, let's look at those first. The general solution we have for something like this, if we're going to be using that Fourier series expansion, let's see what our x of t looks like. And it's quite lengthy here, but this is from the slides. We have the homogeneous part at x naught, because we do want the total solution, e to the negative omega n zeta t cosine omega dt minus phi naught plus a naught over 2k plus, then this is going to be the particular solution part, is the a naught over 2k, and then this summation from n equals 1 to infinity. And I don't want to write the whole thing out, so I'll just leave it here. This is that summation part that we saw in the previous example and that is on the slide, so I won't write it out in detail here. But the thing is, we want the total solution, so we want the homogeneous part, which I will mark again here. This is the homogeneous part of our solution, and then the particular part, which is also the steady state part. So the particular part we know how to solve for. Then we're going to add that to the homogeneous. Then we're going to apply our initial conditions to it. The particular part is going to need this R, it's going to need the phi sub n's, it's going to need a lot of those terms. I'm going to solve those in MATLAB since it's very repetitive, but some of the parameters we do want to find beforehand that we're going to need for the homogeneous part and or the particular part. So natural frequency, definitely going to want that. So we have root k over m. That is going to be root 4000 over 10 for our natural frequency. Completing that calculation, we get 20 radians per second. We are going to need our damping ratio, which is c over 2m omega n. C we were given, going back up, that was the 220. M was 10 kilograms, and the natural frequency is 20. So if we compute this, we get 0.55, which tells us that we do have an underdamped system. We needed to know that because the homogeneous solution we're using is for an underdamped system. So I kind of assumed it was underdamped while writing down this identify step, but we do need to verify that before we can go forward. So it is underdamped, so we're okay there. We are going to need our omega d, our damped frequency, which will take our natural frequency. Since we have an underdamped system, we can calculate this. So the natural frequency times the square root of 1 minus zeta squared, and we get about 16.7 radians per second. I will recopy the omega, that fundamental driving frequency was 2 pi over 5 radians per second. So that was from the Fourier series part, going all the way back up here. We said that the period was 5 seconds, so omega was 2 pi over that, so 2 pi over 5 radians per second. And we want that because we want to calculate that R ratio, which our particular solution is going to need, which is that driving frequency over the natural frequency. We get 0.0628. And we're going to need those phases that are going to vary with n. This I'll do in MATLAB, but just to refresh what it was, the 4-quadrant arctangent of 2 zeta n r over 1 minus n squared r squared. And also for x of t, we need this x naught and phi naught. Those are going to be found after we have applied our initial conditions, and that will not be trivial for this problem, but we will need to apply it to find the x naught and phi naught, which we'll be doing in a little bit different manner, or quite a different manner than we've done in the past. So we're going to have to come back to that after we apply our initial conditions. Now in this one, we were just straight given them all the way back at the top. X naught is 0.02. And V naught, or x dot naught, this is in base units, so meters. And V naught is 2 meters per second. Both of these were given as positives. With the initial conditions, now we can go and solve for x naught and phi naught. But again, it's not going to be simple to do. Going back to our solution, our general solution for x of t here, we know that x of 0 is that 0.02 and x dot of 0 is 2. So we do have these two algebraic expressions that we're going to be using to find the x naught and the phi naught values. But the particular solution is going to depend on how many terms we use. So depending on what the particular solution is going to affect what x naught and phi naught are. If we take more terms, we'll get a different phi naught and x naught than if we take fewer or more terms. Now, because the particular solution is convergent, there's going to come a point where we keep adding terms and it should barely affect what the particular part of the solution is, or the steady state part of the solution is. So it should then barely affect the value of x naught and phi naught. So really a good first step would be, we should see where does our steady state solution converge, how many terms does it take, and use that as a guide for how many terms we should be using when we are solving with our initial conditions for x naught and phi naught. So in this example, I'm just going to use an arbitrary number of terms that's high, and I will assume that that is going to be convergent for the steady state solution. Should go through extra steps to ensure that, but for now I'll just use an arbitrary amount. So what's the process I'm going to use to find x naught and phi naught? That's going to be a little bit tricky here. So once again, I will be using that x of 0 is 0.02 is my x of t term evaluated at 0. So if I simplify that, let me just scroll up back a moment. So I can take this general solution and I can apply t equals 0 to it. So I get x naught, e to the 0 is going to be 1 times the cosine of phi 0, negative phi 0, plus I have a naught over 2k, plus the summation n equals 1 to infinity. Now again, t is going to be 0 in all of these cases. an cosine negative phi n plus bn sine of negative phi n, since the t terms are 0, over the k times 1 minus n squared r squared, quantity squared, plus 2 zeta n r squared. And I am going to call in the code, I'll call this my xp 0. So depending on how many terms I use is going to affect what xp0 is, the particular solution at 0 seconds. So I can find that, and then I'm adding to that x naught cosine negative phi naught. So once I calculate my xp naught, this is going to give me one equation I need to solve, and then I am going to have my x dot naught, which is 2. And going back to the slides, if I put in t is 0 here, I'll get a negative x naught times e to the 0, which is just 1, times my omega n zeta cosine negative phi naught, plus omega d sine of negative phi naught. So that whole thing is multiplied by the x naught term, plus, now here I have my, the a naught over 2k goes away. I will have sum of n equals 1 to infinity of n omega, because I'm differentiating this part as well, negative an sine negative phi naught, plus bn cosine of phi naught, it's a little cramped, over that k times the square root. I won't rewrite all of that, but it's the same thing that we had above. And this will be, I will call this Vp naught. So the particular solution for the velocity naught. Right? Again, the number of terms I use is going to affect what Vp naught is, but it is going to be convergent since these are convergent series. So if we see what we have here is we do have these two equations, 1 and 2, and the unknowns we're trying to solve for are the x naught and the phi naught there. Now the way it's set up here, there's other ways we could go about solving this. I'm going to present one method, numeric method for doing it. It's going to be really hard to do by hand because we have one of our variables trapped inside a trig term. It's on top trapped inside a cosine, and then in equation 2, it's trapped inside a cosine term and a sine term. But what we can do is solve it numerically. What we've done in the past where we wanted to solve an algebraic equation numerically is we used f0 in MATLAB or some root finder. And that works great typically. However, f0 only works on single variable functions. Here we have two variables. It's a multivariate. We have two equations, two unknowns. f0 only will work on one equation and one unknown. So unfortunately, f0 is out for this. But what we can do actually is use an fminsearch. So we can actually minimize a function because fminsearch is going to work on multivariate functions. But we're going to have to do it in a somewhat tricky way in order to solve this nicely, because we want to convert these two equations really into one equation. So what I'm going to do first is I'm going to take my equation 1 and rearrange it a little bit. I'm going to do it as 0 equals, so kind of similar to how I use the f0 plus xp0. And so that's my, I'll call it 1a, I guess. And my 2a, I'm going to take my equation 2 and do, oh, and I forgot the whole point of this. I subtracted 0.02 from the left-hand side so that I have a 0 on my left-hand side. Right? And then that 0.02 made its way to the right-hand side. And my equation 2, I'm going to take that negative x naught omega n zeta cosine negative phi naught plus omega d sine negative phi naught plus vp0, and I want to take that 2 to the other side. Really, I'll do this in a more, I'll write this in a more general way so we can see what's happening. So I'll subtract x naught, and here I'll subtract v naught. But we know that this is 0.02 for this particular case, and this is 2 for this particular case. But this is, in general, what I want to be doing. All right, so I'm not quite there yet, but what I want to do now is I am going to use just this part. So the right-hand side of this, and just this right-hand side as well. All right, so I'm just taking this expression, and just for shorthand here, I'll call this A and I'll call this B, just so I don't have to keep writing out this whole thing. So I still have two equations, 1a, 2a, that must be satisfied simultaneously, but now at the moment I have these two expressions. I'm going to be using A and B, which is the right-hand side. So what I can do is actually find the minimum of a function using, well, in MATLAB I'll be using fminsearch, but this is good for any minimization routine. So I can use fminsearch of, so I want to minimize using, so I'll define some function here. Let me just call it, I guess, q. Q is going to be x naught phi naught. So we can see what it's going to be doing in the code. All right, so everywhere I have an x naught is going to be q of 1, and everywhere I have a phi naught is going to be q of 2. But that's just the way fminsearch is going to be working. So I want to take a squared plus b squared, the square root of that. That's the function I want to minimize. Now I'll be using something a little bit different in MATLAB. I'll be using the norm, which actually we've seen before. So I want the norm of A and B is going to be involved here. And that does the exact same thing. It's going to square each element and then take the square root of it. And I can give it some initial conditions or initial guesses on what x naught and phi naught are, and I can get my result. Right, so what's going to be happening here, this has to be in parentheses. The reason this will work, maybe it's not the most efficient way to do it, but the reason this will work is it's going to try different values of q, where q is the vector of my x naught and phi naught. So it's going to try different values in A and B until it's minimized this function, the square root of a squared plus b squared. Well, when is this function going to be minimized? We want to think about that for a second. Well, I'm taking the square root of something. The square root at least we're only going to be using real numbers here, the smallest the square root of something can ever be is 0. So it's trying to find when is the square root of this thing 0, since that's its minimum. A squared, if we look at how that is up there, well, A itself is going to be minimum when my x naught cosine negative phi naught plus xp0 is equal to the given x naught, that 0.02 in this case. If I find an x naught and a phi naught that produce anything but 0.02, then A is going to be something that is not 0. And then I'm going to square it, so it's going to be some positive number. A is the smallest when my x naught and phi naught make that expression equal to 0, meaning that I have satisfied that initial condition. The same thing is true with B. When my x naught and phi naught satisfy that expression to be 0, that means that I am equal to my v naught, and that's satisfied. So if B is anything but 0, I'm going to square it, and it's going to be a positive number. So the way I'm going to find the minimum that when this is 0 is only going to be if A is 0 and B is 0 simultaneously. And when that happens, that is only going to happen when I found the x naught and phi naught that satisfies both expressions at the same time. So effectively, I am going to be doing a root finding, but in 2 dimensions, among 2 variables. So it's definitely trickier than trying to use F0. It's a little bit of a kludge or a hack in order to do it, but this is a way that it's going to keep trying those different values of Q until it finds the one that minimizes that function, thus satisfying both initial conditions in both equations simultaneously. So let's see what that looks like in MATLAB. Going into MATLAB, we can recreate a lot of these parameters that we already had solved for. So all of this given information of m and c and k and the x naught and v naught, calculating the parameters from the parameter section, and we can see what we have so far, and making sure our function is correct. All right, so that's just a plot of our function. Now we can put in our a naught, an's, and bn's that we already found using Mathematica. So those are now in and defined. The R and the phi definitions that we had. And then we can define our particular solution. So these are coming just from those slides. This is what I wrote down. So this is defining the nth value of the particular solution for some value of t. So like I said, the first thing we're trying to find here are those initial conditions. Or apply our initial conditions to find our x naught and our phi naught. So I'm going to calculate these. So this xp0 and xpd0 are those xp0, and I should call it vp0, but that's the same thing here. And I'm doing it just to be on the safe side here. I'm going to do it for the partial sum 1,000. So I'm going to go up to 1,000 terms. This is probably way more than I really need, but I just want to be on the safe side in this example. And then I've calculated those xp naught and xpd or vp naught like I had before. This is where now I am doing this minimization routine. So if we see how it's working here, I'm doing the fminsearch. I'm actually calling it big X here instead of the Q, but it means the same thing. That is my collection of big X naught and phi naught. And I want the norm of, this is my A expression here, uses the initial position, and this is my B expression from the other part that is satisfying the initial velocity conditions. And so that's, by using the norm, I'm going to be finding where is the smallest value that this squared plus this squared is. And that we know is going to happen when at 0. It must be 0 is the minimum of this because I'm taking the square root of 2 positive things. So the smallest that can ever be is 0. And then I'm going to give it these initial guesses. I'm going to guess that my x naught, big X naught is 0.25, and my phi naught is a little bit more than pi. When we're doing fminsearch or even F0, I'm going to suggest, especially if you have angles, avoid having your initial guess be a special angle like 0 or pi over 2, because sometimes the routine can just get stuck when you have one of those special angles there. So that's why my initial guess here is a little bit off from pi, to ensure that I'm not accidentally falling into one of those special angles when I'm doing this. Now, if I see my left-hand side, what is it going to be giving out to me? X naught is going to be the values of big X naught and phi naught that satisfy this, that minimize it. F is the value of this function when it's minimized. And then flag tells me about the convergence. Did it successfully run? So this is a good indication of, don't necessarily just trust the outputs of it. We want to make sure that it ran correctly. All right, so in theory, F should be 0 when this runs successfully, because it should find when my norm is 0. But let's see what happens here if I run this. Okay, so it is giving me down here that my x naught, big X naught value 0.1169, and my phi naught is 2.687 about radians. And it says the value of f, the value of the function that I'm minimizing, is it's not 0, and it will never really be exactly 0. We can never find the exact super precise values that make it exactly 0. However, we do get a very small number here, so that means it probably is doing it correctly. If we got a number here that was like 5 or 50, it's probably not running correctly. And also this flag value I have comes out to 1. In general, if it comes out as 1, that is an indication that it converged to a solution, not necessarily the correct solution. That's why we also want to check little f here, but it did converge. If we get a 0 or a -1 or some other value, that means that something went wrong along the way. So that can happen if our initial guess is just bad. It might not converge. Or if it goes to like an imaginary value, we might get a flag there that is not 1. So the flag and f are ways to, again, just check our answer a little bit. But here, the 0.1169 and the 2.69 appear to be good values for the x naught and the phi naught. Now keep in mind, this was done for 1,000 terms when I was calculating the particular solution evaluated at time is 0. But now I can go all the way back here and fill in that missing information. So we have the value for x naught and our value for phi naught. So again, those are coming from that fminsearch, kind of that lengthy thing that we had put together. So we have our x naught, phi naught. Now our general x of t solution we have. I'm not going to rewrite it since it's pretty lengthy here, but we know all the pieces of it. So we're now at the assemble step, but I'll just assemble it in MATLAB. X naught is found, phi naught is found, all of the parameters are found. Now we know our x of t. So I put it together, do the assembly in MATLAB. I'm going to do this for 3 forcing cycles. So we see on the time span, it's 3 times really that period, which is 5 seconds. So 15 seconds I'm going to simulate this for, and I'm going to put this all together here. So in this for loop is where I'm using assembling my particular solution. That's where I'm doing that summation. And then I can put together, so this is here, the particular solution step. And then I have my homogeneous solution now that I know the x naught and the phi naught from using the initial conditions. And then my total solution is going to be the sum of my homogeneous and my particular. So let's run up to this point to see what our solution looks like. All right, so this is kind of a plot in progress because we're going to add stuff to it in a little bit. But we see here I'm pulling out, at least looking at the code, the 10, the 100, and the 1,000 term solutions for x of t. Now, keep in mind that my initial conditions were found using the 1,000 term solutions, so the comparison I'm making here is not necessarily the greatest, because technically I should have found a different x naught and phi naught when I only used 10 terms in the particular solution, and then a different one when I used 100, but it's going to be fairly close here. But if I look, the green is when I used 1,000 terms, The blue and the black is when I used 110, respectively. So we see here the green solution for our x of t looks pretty smooth. We have kind of this overshoot, but it appears to be good. If I zoom in, we see the blue and the black are kind of on top of each other. And if I zoom in a little bit more, we see that the blue and the green, the 100 term and the 1000 term, are basically on top of each other. We see maybe the blue is a little bit more, has a little bit more artifacts, a little bit less accurate or precise near these step-offs, near the discontinuities than the green is. And then the black, where I only use 10 terms, not very good. We have these artifacts here where it looks like the mass is going to be oscillating, but that's not actually what's happening. That's from not using enough terms. It's not actual oscillations. If we look at the green and the blue, we do see an actual oscillation when the force is first applied. That is not an artifact of not using enough terms. That's a true oscillation of our object. All right, so using 100 terms or 1,000 terms looks about the same. Using 10 is too few. But what we want to look at also is, how do we know this is correct? How do we know we've used enough terms? Well, we can use different types of convergence ideas like we used in the previous example, where we can see what happens if we keep adding one more term, one more term, one more term. How does the root mean squared error between them change? When does it drop really, really small? And that can be an indication of, yes, we're using enough terms. As we keep adding one more term, there's barely any change in the result of the graph. However, another thing we can do is we can compare it to another way of getting the solution. In this case, we don't yet have another way of getting the exact solution. We actually will later. But what we can do is do a completely numeric solution, numeric in the sense of using an ODE solver, like in this case, we'll use ODE 4.5. So what we can do is we can make our state space model for this function. Now it's a simple spring mass damper system, so we've done this in the past in system dynamics at least. But what I can do is I can put in my forcing function. Here, because it repeats itself every 5 seconds, I'm using that modulo to make sure that f is repeating. And then I am making my state space model like I've done before. So I am defining my state variables x1 and x2 as the position and the velocity, respectively, of this mass. So putting this together, I know that x1 dot is the same as x2, and that x2 dot is going to be 1 over the mass times negative c times the velocity minus k times the position plus f. And that f, notice, is also getting divided by the m. So this is coming just from rearranging the equation of motion and putting it into state space form, which again, we've done before. And this is a linear system on the left-hand side, and then we have this piecewise forcing function. So the numeric solution should do pretty well with this, and we'll see what it does in a second here. All right, so this is the state space model, driver 5.2 I'm calling it. And when I go back here, I am going to use here ODE 4.5 on that state space model. And I'm going to do it over the same time span, those 3 forcing cycles. And the nice thing is here, I can just plop in what those initial position and velocity is. I don't have to go through that fminsearch when I do this. However, I'm not getting a closed form solution when I do this. So let's compare, before we get to the RMSE, let's just look generally, what does the numeric solution look like when I put it on top of those other solutions that I got with the closed form. And here it is. All right, so the numeric solution is that red dashed line. So let me zoom in on what I have here. So if we see, we can see pretty well that red dashed line is pretty much directly on top of the 1,000 and the 100 term closed form solution, and certainly looks different than the 10 term solution. And I can keep zooming in. I see only pretty minor differences between here. I see the 100 is a little bit lagged behind, and the amplitude maybe is a little bit different, but the 1,000 and the numeric are basically right on top of each other. Now, the numeric solution I am going to take for this problem as the true solution, or very, very close to the true solution. But using an ODE solver is not necessarily going to give us the correct solution either, so we do want to be careful there. But if we're using these basically two different approaches and they are graphically giving us the same solution, then we can probably trust that both of them are going to be correct because they're agreeing with each other. That's not always true, but if we can take these two different paths and end up at the same place, that's a pretty good place to be in trusting the solution that we're getting. And then quantitatively, I am going to compare the root mean squared error between the ODE solution, the ODE 4.5 solution. Again, I'm going to call that the true answer in this one. And then what happens as I use more and more terms in my exact solution, using more and more terms in that partial sum. That'll be the last comparison I want to make here. All right, so this is what I get for the root mean squared error between what I'm accepting as the true solution and using ODE 4.5 and the partial sums. So if I see here, even by the time I get to 100 terms, look how small that root mean squared error is. And that's what we saw graphically, is that the 100 term and the 1,000 term solutions were basically in direct agreement with what we saw from the ODE 4.5 solution. Whereas when we used only 10, we had at least relatively that higher RMSE error. So if we, right about here where that RMSE basically flattens out, this is telling us that using 30 terms appears to give us really good agreement with the numeric, the ODE 4.5 solution. So 30 terms in our analytic solution is basically enough to trust the answer that we're getting in the end. So finally, recap this pretty lengthy problem we had to go through. We had to go through the modeling step. We actually didn't have to find the m, the c, and the k. That was given to us, but that would have been another step we had to go through otherwise to do like the Lagrange equations to find the equivalent values. We were given graphically what the forcing was, this periodic forcing. So we came up with the piecewise function that described it, and then took that piecewise function and did the Fourier series expansion on it. We saved time again by using Mathematica rather than doing it by hand, but we found the coefficients of a0, an, and bn. Then we can put together our equation of motion. I just left f of t on the right-hand side, and in the identify step, it is not given to us as a simple harmonic function. This is falling under this general forcing category, where we are using the Fourier series expansion approach to solve it. So we know what the general solution should look like, this homogeneous solution plus the particular solution. The particular solution is coming from the Fourier series expansion. The homogeneous solution is coming from the fact that the left-hand side is a second-order system with damping. And we did initially assume it was underdamped, but then through the parameters, we did demonstrate that indeed it was. The zeta value was between 0 and 1. So we found relevant parameters to put together our total solution, well, the homogeneous part and the particular part separately. Then using our initial conditions that were provided to us, we, in a kind of roundabout way, found the big X naught and phi naught that we needed for our total solution by applying these initial conditions. So we had to solve these two nonlinear equations simultaneously for X naught and phi naught. And we did that using this kind of hacked together fminsearch routine where we could solve for those values and satisfy both equations at the same time, since f0 does not work on multivariate, multi-equation expressions. So from the fminsearch routine, we were able to find our big X naught and phi naught 0.1169 and 2.69 respectively. Using those values, then we could assemble our total solution and find our x of t. Right, so that's the assemble step, which we did in MATLAB. We put together the whole solution in MATLAB, and the solution quality will depend on how many terms we use in that summation. So here, just as a sample, 10, 100, and 1,000 terms. The 100 and the 1,000 look basically the same, and we compared it to a numeric solution with ODE 4.5 and saw really good agreement with the 100 and the 1,000 term with the numeric solution. Going a little bit further and looking at convergence between our fully numeric solution and our partial sums, we saw that by the time we used 30 terms in our partial sum, it looks like we've converged to a relatively low error solution to our problem.